Hi, everyone. Thanks for inviting me to present today. I will be talking about estimating oxygen in the Southern Ocean, leveraging oxygen observations, but also temperature and salinity data and data science methods. I will introduce two different approaches. The first one is something we did a few years ago with Slava Lipcic and Matt Mazelov, and we are considering revisiting now, so your feedback and suggestions are very welcome. Of course, your feedback and suggestions are very welcome for the second approach I will be introducing briefly today. This is leveraging multivariate Gaussian process regression to deal with the same problem. And I would like to mention that this application of multivariate Gaussian process regression to BGC Argo data is led by Alison Gray at University of Washington. Michael Kuzala and myself worked on this with her and their student, Jamin Wan. So why do we want to study oxygen in the ocean? It is key to study the variability of oxygen in the ocean on different time scales to monitor the health of the marine ecosystem. It also helps us better understand how the Earth system is changing in a changing climate. What has been observed and what models also show is that oxygen is decreasing. It has been decreasing in the past several decades, and it will continue decreasing. Since 1960, this paper by Schmidtko et al. Shows that oxygen content decreased by more than 2%. We see these red patches in the map here showing the oxygen decrease. So red is decrease. But we really want to study oxygen at different time scales from seasonal to interannual. And even for the seasonal time scales, there haven't been historically very good observations. If you think about ship measurements, ships don't go out in winter as much as summer, so we have a seasonal bias in that, besides having sparse measurements from ships observations. So I already, while briefly motivating why we want to study oxygen, I showed a map. And so why, that's how we think about the ocean, how we study the ocean. We look at a map of these fields, but how do we observe the ocean? It's quite different. We go out there, or we don't go out there, like in the case of Argo floats, but still measure at a specific point and time. So the Argo floats, if you're not familiar with the Argo program, are autonomous floats that spend most of their time around 1,000 meters in the ocean, and they drift with the currents. And then every 10 days, they go down to generally 2,000 meters. This is what most of the Argo floats out there are doing now. There is a pilot program, a pilot mission, Deep Argo, that wants to go deeper, and hopefully we will see more of these deeper profiles in the future. But for most of the profiles we have so far, the floats go to 2,000. On the way up, they measure temperature, salinity, and pressure. And on the surface, they transmit the data to the satellite. Based on which transmission system they have, they stay shorter or longer. With the newer one, they stay shorter, which is a good thing. And then they go back. I said they measure temperature, salinity, and pressure. This is, again, what most of the floats out there do at this point in time. But there is a part of the array that is actually measuring more, is measuring ocean biogeochemistry. This is very valuable, obviously, and likely we will see more and more of these profiles going forward as the Go BGC project has been funded and plans to put more of the BGC floats out there. But what we have so far are relatively few observations of biogeochemistry, specifically oxygen is of interest today, and many more profiles of temperature and salinity. As I said, we want to go from scattered observations in space and time to some regular space-time grid, because that's how we study the ocean. How can we do that? We can think of merging the information that we get from observations with our understanding of how the physics and the biology work, so the equations, and through data simulation, state estimation, we come up with a map. This actually comes from the Southern Ocean State Estimate, SOSE, that you may know as SOSE. We can go about it just from an observational point of view, using only observations and data science methods. And that's what we will focus on today, even if, as you will see, we'll leverage the Southern Ocean State Estimate. So as I mentioned already, we have way more floats, way more profiles since the Argo program started that measure temperature, salinity, and pressure than biogeochemistry. Just for you to have an idea of how it would look like if you were to plot on a map, which is what's happening here behind me, all the profiles that were taken in a 3-day window at some point last month. The yellow dots are the profiles that measure temperature, salinity, and pressure. Most of them are yellow. Most of the dots are yellow. We see green dots at some locations. Those are the floats, the profiles from floats that measure ocean biogeochemistry. There are some dark blue dots. Those are the deep profiles I was talking about. But the idea is, can we improve mapping of oxygen using the information from temperature, salinity? So the first approach I will talk about is using random forest regression. And when we did this, we wanted to not only try the method on actual observations, which eventually is the goal, but also have a way to test this method in a setting where we knew the truth, in a model setting. So we could use the biogeochemical Southern Ocean state estimation, state estimate that you may know as BSOSE. At that time, the iteration that was available was for these 5 years, 2008 to 2012, which reduces the number of profiles that we can use if we want to do this both in the real world and in the model world. But on the other side, it lets us test the method in the model world where we know the truth, obviously, but with this model, which assimilates observations, we also have the model profiles. So the model stores the value of the model fields at exactly the same time and location of the real profiles in the ocean. So that's really convenient to test the method. We looked at comparison of what we got with the World Ocean Atlas. This is what people normally use to look at biogeochemistry in the ocean, what they have used before Argo became available. As I mentioned already, the data are sparse from ships, especially in winter, because there are not as many ships out there. So for the data that we did use from Argo, we have here the number of profiles in 1 degree bins. And on the right, these are the profiles that have Argo temperature and salinity. And as you can see, we have much better coverage than the profiles that measure Argo oxygen, that measure oxygen from Argo. One good thing that is different from the World Ocean Atlas is that these profiles are there both in summer and winter. So we don't have that seasonal bias, except that for the winter, in regions where there is sea ice coverage, the float cannot come out at the surface and communicate with the satellite. So it still collects a profile, but we don't know exactly where that profile was collected. So the target, our variable to estimate, was oxygen. So we did this as a proof of concept. We looked only at oxygen at 150 meters. And we used as predictors those variables for which we have a large data set available: temperature, salinity, latitude, longitude, month, and year. The random forest regression leverages basic elements that are basically the regression trees. And there are ways for each tree to be in the forest to be different from the other. I'm happy to chat more about that if you're interested. But the point is that at the end, when you train this forest of regression trees, you can then estimate, predict oxygen at the locations where you don't measure oxygen, but you measure temperature and salinity. Some diagnostics is also possible using this method. One I will show here shows the permutation-based importance of the predictors. Basically, how much your result cares for each of these predictors. And this is shown on as the vertical axis is basically the difference in mean squared error between predicting with the forest that you trained and doing a random permutation of each of these predictors. If the predictor doesn't matter at all, then it doesn't matter that you do the random permutation. You find low values of the quantity that is shown here on the vertical axis. These are micromole per kilogram squared. So the two main predictors, and this is consistent between training the forest with actual profiles from ocean observations and model profiles, are salinity and temperature. And this is what we were expecting, because it's consistent with water mass dynamics, which is important in interpreting the map that comes out from this process. So I should say that what we predict is oxygen at the location of temperature and salinity that we observe, and in the case of the model, sample the temperature and salinity sampled from the model at the location of the actual observations. Then we have to go from there still to a map, but we have at that point many more observations of oxygen or predicted oxygen to put together with the actual observations. And we do that mapping VLE square fit. So when we do this in the model world, as I said, we can actually compare with the truth. And when we do this in the model world, we don't even, of course, we also try with like predicting at the location at TS and then mapping with this least square fit method. But we can also just say, now we have trained the forest, we'll predict oxygen at all locations from the model where we know temperature and salinity. So we only focus on the differences from the truth that are due to this random forest method. And we get when we take a difference for the annual mean between the true SOSE, so SOSE is the model, Southern Ocean State Estimate, minus the random forest based estimate, we see that the error is less than 1.5% in a large part of the domain, 65% of the domain for the annual mean oxygen. There are still large biases in some regions, because not all the regimes are sampled from the observations that we have available of oxygen. In particular, there are boundaries, and oxygen will be low there that are not sampled at all. So we don't expect the model to do well there, and it doesn't. In general, also the regions where the RF method doesn't perform well are those regions where the variability is high. And you can see that comparing the map on the left, that is the difference I described, the difference with the truth, with the map on the right, that is the standard deviation, the variability in the model. Of course, now we can go on and predict at the actual temperature and salinity values that we have from Argo, do the least square fit to get a grade, and we get the map on the left, where we see this band of high oxygen that is consistent with subduction of Antarctic intermediate waters just north, that starts north of the polar front of the Antarctic circumpolar current. So we see features that we expect, which is good. We can also take differences between the map that we get from observations and other products, including SOSE, obviously, but also the World Ocean Atlas maps. So for SOSE, when we do this difference, and if we focus only on the patches of colors, because we want to mask this map based on what we learned a minute ago about regions where the RF method does not perform well, we see that there is some positive, negative, and strong positive difference between our estimates from observations and the model. And again, for instance, this large positive value is associated with a known bias in the model. The model here overestimates the annual mean oxygen. So this is helpful to compare and see what other products are doing. We can do this for global zonal averages. In this plot, we have the annual mean oxygen on the horizontal axis. Vertical axis is latitude, south to north. And we have a bunch of different lines for SOSE. And the reason why is because we want, of course, the truth, which is the dashed black. We want the RF-based estimate from SOSE profiles, from model profiles. So we want to see how that compares to the truth. We also want to see the effects of that least square fit I mentioned earlier. We said we have to grid. We have to go from these point predictions to the grid. We do a least square fit. We can do the same least square fit with the actual oxygen from the model at the temperature and salinity location. We have that, so we can do that. And if that is different from the truth, it means that the least square fit itself has some effects on the comparison. But luckily, all these lines, at most latitudes, collapse one onto the other. So that gives some confidence that the RF method can actually represent well the truth. And we see that in the comparison between the red line, that is instead the estimate from the Argo observations with the RF method, we see that the model, SOSE, tends to overestimate this global zonal average of the annual mean oxygen. Also for the World Ocean Atlas, there is some disagreement with Argo. The period, of course, is different. And as I said, there is a seasonal bias in the World Ocean Atlas, but I still wanted to look at how the two compared. We can do the same for the annual anomaly of oxygen. And here now, while we see that the dashed black line, so again, so this is the month on the horizontal axis and the O2 anomaly on the vertical axis. So let's look first at the lines for the model. And in the previous slide, I said all the lines for SOSE were collapsing one onto the other. That's great. It means that the method performed well. Here we see that the dashed line, which is the model truth, and the gray dots that are basically an estimate from applying the least square fit, so the gridding part only of our method, to oxygen at the location of temperature and salinity. So we have that from the model. So that part goes well. The two agree with each other. But then the RF-based estimate underestimates the signal, underestimates the annual anomaly. And this is again due to the fact that we are not sampling everywhere, and not all the regimes are represented in our in the samples that we have available. When we do the same thing to look at the annual O2 anomaly from observations, we see that we know at this point that our method may underestimate that variability, and we see that it's similar to the true model. So we know that the red line may be underestimating based on what we learned from doing the same, applying the same method to the model profiles. So it may be that this is telling us that the model itself also underestimates the annual variability. Again, I showed a line from the World Ocean Atlas. Something funny is happening here, but no surprise. As I said, there is a seasonal bias in those observations. They are sparse, and they are sparse especially in winter. So to summarize this, what the community wants really is, the long-term goal is to have more of these observations of ocean biogeochemistry, oxygen and other variables. But what do we have now is much fewer observations of biogeochemistry than physical variables. So how can we leverage that to better estimate oxygen? For instance, we can use, among other things, a random forest framework, as I showed here, and this can help in the meantime while we don't have more observations. And even when we have more observations, there is information in the temperature and salinity fields that can be leveraged and should be leveraged. Also it helps us identifying biases in current products. I didn't speak about this today, but this kind of framework can also help strategize on how to deploy the new floats that are going to be out there in the future, thanks to the GoBGC program. It is important for all of this to work, as I mentioned earlier, to have a sampling that represents well all the statistical regimes that are relevant for the problem. We saw the large bias in the eastern boundaries. So possible steps to look at next, if we revisit this problem, would be to, number one, put uncertainties on other estimates. When we do that, when we apply the method to the model, we can have some idea of how that differs from the truth, but we would want formal uncertainties on our predictions. So we could use satellite data along with global in situ observations of temperature, salinity, pressure, and oxygen, not only at one level as we did for the proof of concept, but at all other levels. And we explored a bit with satellite data, but we didn't get an improvement that would justify the complexity, the additional complexity of the model, adding those predictors. So we stuck with our 6 predictors. We could, as Micah presented, look at relevant regimes for the oxygen variability in the model, and that would be an interesting thing to look at. We could use other machine learning methods, and any suggestions you have, we are happy to hear, of course. Now, with the remaining time I have, I want to introduce this proof of concept we're working on using multivariate Gaussian process regression for the same problem. Again, there is the same constraint of limited oxygen observations compared to temperature and salinity. I showed you this map. I show it again just because now we are doing this with a different time period, more recent period, more data. So if these are all the dots that have oxygen, and as you can see, if you recall what I showed in the beginning, we have many more oxygen data. Temperature and salinity, we are doing well, and we were doing decently well earlier as well. But in here, we want to leverage the autocovariance within the BGC field and the cross covariances with temperature and salinity to do this mapping. So we can do, and I will describe maybe the steps in a second, but just thinking of the general idea, we have a grid point where we want to estimate our oxygen. We have observations. Some of them have oxygen, temperature, and salinity. Some of them have only temperature and salinity. We want to do a weighted average of the nearby data. And this weighted average will depend on the autocovariance in the field of interest and the difference between the distance between the data point and the grid point, and the distance between data point, and of course the cross covariances with other variables. So how do we model this? So the first step that we take, and this is done also with univariate Gaussian process regression for physical variables, we remove some mean field. So the mean field we remove for the univariate case is the least square fit to second order polynomials of latitude, longitude, seasonal harmonics in times. For BGC, we also want to include temperature and salinity when we estimate this mean field. And once we have this mean field, we remove the mean field from the full measurement, and we end up with these residuals, these anomalies. And now we need to model these residuals using leveraging the autocovariance and the cross covariance in temperature and salinity and the BGC fields, in our case, oxygen. For our auto and cross covariances, we use a Matern structure with properties as described by Kleber and Nitschke, 2012. We use a local window approach where we estimate these parameters for the covariances in windows, moving windows, and using maximum likelihood estimation. Similar idea to Kuzel-Einstein, 2018. And so what we do is to actually first fit a univariate Gaussian process to temperature and salinity to estimate the parameters, leveraging the multitude of observations of temperature and salinity in the ocean. Once we have those parameters, we go on to estimate the covariance parameters for the BGC variable, for which we have limited amount of observations. In this case, it will be oxygen, and also the correlation coefficient across fields. Finally, at this point, we can predict the BGC field. So let's think of oxygen, for instance, at all the points where we have observations. So not only where we have oxygen observations, but also where we have only temperature and salinity. So I'm running out of time here, but I just want to mention that we haven't tried this with real data yet, but with real BGC data yet, but we tried with simulated data. And what we saw is that we have the most benefits. So this setup was just to simulate two correlated fields. So we knew the truth. We didn't do this in a model. We just made up data. We knew the truth. So the correlation between fields and the covariance parameters. So length scales in space and time, variance. We tried doing either univariate Gaussian process regression on the sparse oxygen data or oxygen-like data, or doing bivariate Gaussian process regression. And we see that there is an advantage of doing the bivariate Gaussian process regression. And this advantage is larger when the difference in number between the two groups of observations, so those where we know everything, including the BGC variable, and those where we only have temperature and salinity, if this difference in number is larger, then we see the most benefits of the method. Couple of other things, I'll not go through the graph, but I can come back. The benefits depends, of course, on the correlations of the fields that we are using and the signal to noise ratio. It's also important to include correlation in the noise between variables. Like in the real world, we measure we take these measurements from the same float. So we need to take account to the cross-correlated noise. And what I mean by noise is not so much the instrument error right now, which we should probably include for the BGC variable, at least is very small for the temperature, for instance. But I mean the scales that are not resolved by the Argo array. So as next steps, we'll try this on real data. And even before that, we'll do something similar to what I showed for the random forest approach. We'll try this into the model world where we know the truth and we can compare. Alison plans to make the final estimates when we have them from the actual Argo observations available on the Microsoft Azure cloud. Just very 10 seconds advertisement of another related project. If it's of interest to anyone, please reach out. I'm happy to chat more about this. Today I focused on this application of the multivariate Gaussian process regression for BGC mapping, but we are doing this also for physical variables of the ocean. And Michael Kuzel and myself will focus on improving mapping of physical variables of the ocean, including doing multivariate Gaussian process regression, improvements to the model to include the vertical dimension, which now is not done in other estimates. And especially one key part of all of this is to put uncertainties so that we compare with other products and we do studies from these fields. We have uncertainties that we can rely on. I'll stop here and I'm happy to take questions. Thank you. Thanks so much, Amanda.
Any questions? No?
Yeah, thanks, Donata. That was great. So you showed us how to reconstruct fields like oxygen. You start thinking about other biogeochemical properties, say carbon. So anthropogenic carbon and the passive heat in the ocean are actually quite correlated with one another. So I guess that could be something that can be reconstructed that so far has been done with kind of very ad hoc, decomposition of its biogeochemical properties.
Yes, yeah, that's a great point. We started from oxygen because it's well observed, relatively well observed, even sparse but well observed, and also better constrained in terms of measurements. So we started from something that we think it's easier to deal with, and then it can be extended to other things, and it should be extended. It's a great point. Yeah.
Yeah, no, I think that's great. I think one thing that might be kind of doable is starting from the model world.
Yeah.
Right?
Yes. Yeah.
So we could actually kind of try to use the methodology, try it within the model world, and see what we're getting. And you can also do error bars, right? So it gives you an idea of already how you could extend it.
Yes. Yeah. That's a great point.
Because it's a pretty good. That's a way we look at how the stratification has changed and how much heat goes up in the oceans, and that
yeah. No, that's a great point. Yeah. Thank you.
Go ahead.
Thanks. I was curious if you could say a bit more about how you think the results from the first project might contribute to future Argo missions, whether it's targeted certain locations, or if you could just talk about that a bit more. Thanks.
Yeah, that's a great point. Like let's see. I should have a map. Yeah, I think I do have a map. I don't have the previews. Okay. I just flip through slides. Sorry about that. So one thing that can be done in the model world, and we did partially in this proof of concept that we did at that point, is to say, okay, the black dots in these maps are where we have oxygen data. This is where in that period of time we had oxygen data. What would have happened if we had observations in these eastern boundary regions, here and there, where the method didn't show to perform very well? And sure enough, if you put observations there, you sample those regimes, the model does better. Word of caution, you also don't want to oversample those specific regimes, otherwise the model again will do worse. But this kind of approach can be used, and we tried, different regions where we added artificially some floats to see how things improve. So this could be used to, that's what I meant when I said this could be, this approach could be used to strategize, would be adding information to that process of making a decision of where to put the new floats. Basically doing it in the model, doing it in a way that makes sense, like adding a float. Of course, if you, and we tested with that just to show that if you just could go out there and say, okay, I'm gonna just, put floats, profiles everywhere, which you can do in the model, but then is that what is gonna happen? In life, what happens, you put out in the float. So then you have to, follow the floats and the profiles that are feasible. And that's why like this, kind of, the red dots are from fake floats. So you have to be, mindful of how you do that, but you could use this approach to say, if we put 3 more floats, 4 more floats per year or whatever, how much it will improve the end result.
Thank you.
Can I sneak in a question there? I mean, SOSE is an adjoint. So have you thought about, at a lower resolution, perhaps exploring that in terms of float deployment?
So yeah, that's how these tests were done in the model world. So not, this is nothing operational, it was just a proof of concept. But how
I mean, exploring the adjoint.
Oh, you mean to deploy floats in the model to keep track exactly of where they could go? So yeah, that could be an option. An easier option is to say, now I'm going to say that in these 5 years, this number of actual floats that in reality only have temperature and salinity, now I give them also oxygen. So it's easier, right? Since you have those floats, and say, what if we had this amount of floats that instead of only measuring temperature and salinity also had oxygen. That's an easier way, but yes, the floats could be deployed technically in the model, as you said. And
sorry, I snuck ahead.
Oh no, good.
But how complex is the relationship between temperature, salinity, and these biogeochemical variables that you're interested in?
So the relationship is nonlinear, and there is a lot going on. So there is, the solubility aspect of this. There is the water mass dynamics. All of this, we hope that the machine learning method can pick up and, do a better job, even for the parts that, the solubility. There are some relationships out there, but they have problems, of course. And so can the machine learning method try to describe all these things that are happening?
Because I remember Mikhail was trying to build that somehow in these spatial models. He had thought about ways of doing that directly, so you can leverage more than the correlation. Right? Yeah.
So we have thought of that, of taking account of the solubility aspect, for instance. But talking more with biogeochemists, there are uncertainties associated with those relationships. So we stuck to keeping everything and hoping that the machine learning method would describe. Yeah.
Okay, and then for your second project, I remember he was also thinking about using distance in 3D in complex ways, where you look at vertical distance different than horizontal distance. Did you make any progress on that?
So this, we haven't yet worked on the vertical component of this, but this covariance for now, we only map one level at a time at this point in time. So also for the physical variables, like ocean, you may be familiar with the oceanic content work that we're doing with Mikkel. In that case, we just look at two different levels, just because the amount of data changes as you go deeper. We don't look at, the vertical dimension. But that's, definitely something that is part of this NOAA project, to include modeling basically that vertical dimension.
With more data, you probably have a shot of really getting at that, right? With more Argo data, maybe.
I mean, now we have definitely the data. It's just to add that part to the model. We have the data for sure, Annalisa?
Somehow related, can you actually get into the machine learning part and kind of separate the contributions? Because of course, one of the big problems we have with models is that we always end up trying to figure it out. The solubility is easy, but everything else is what the models really mess up. And so even just to have an evaluation of what that component is and a map of that would be extremely useful for BCM models, global models that are really doing very different things.
So that's one of the things that, revisiting this problem should include, to get more at the processes that are have a way to actually detect the different processes beyond us looking at the importance of the predictors and other diagnostics that I didn't show today, and see that things make sense based on what we understand of water mass dynamics. But it's a good point, and we want to do more of that.
I think we have a few more minutes left, so I'm going to ask another question. In terms of understanding the water mass dynamics, like Annalisa just mentioned, I'm wondering what motivated your choice of using random forests, for example, because it seems a little bit counterintuitive to do that sort of somewhat cross-chopping and sort of choosing in that way. So could you speak to that a little bit?
So the choice of random forest came up just because we got together with people for a workshop on Argo and data science, and we were chatting of ways of doing this. Random forest came up, and we tried it. What I should mention is that while we were trying random forest for this, someone else has tried a neural net, and it was just an attempt on their end, but from what I've heard, at least they didn't get a better result for just playing around attempt that they did. One thing with random forest that I like is that it's it's kind of robust, like changing parameters a bit doesn't, make a big difference. But I definitely, as I mentioned in the last bullet point, would like to try different methods and explore more because, as I mentioned, someone did try to do that with a neural net, and but only on a, just for fun kind of approach. So
I guess my point was somewhat more directed towards the random forest method itself, where you initially have to sort of draw these very distinct decision boundaries, and having that, you sort of, with the ocean being highly nonlinear, and we spoke to this earlier in a bunch of questions, having a method that maybe is able to be a little bit more subtle in teasing out those potentially overlapping different, covariance clusters seems like something that would intuitively make more sense to me, at least.
Yeah, I see your point, and so one thing I can say is that this is not just one regression tree, where then it would be like a chopping, right? This is a forest of regression trees. So it can describe those nonlinear relationship, and is not, we don't see that kind of, sharp changes just because of what you just say. It's not just one regression tree, it's a forest of trees, and every time we use the sample of the data with substitution, and the predictors are different for every tree. So there are ways of, it's not, just, literally chopping with one regression tree based on salinity or temperature. It's a forest of trees, and then the result is the average. Considering
I guess
trees.
I was speaking to the fact that you do have, like, all of them are trees.
Yes,
so
that's true. But when you put all of them together, you can describe those relationships, and it seemed to work, quite well in this test case. This said, I'm, very interested in trying different approaches and see how they compare.
Cool, excellent. Should we do a changeover now?